Hello, Year 12. This is exercise 18b. We're going to look at something called a hypothesis test for binomial distribution. Look, we're going to do in class a little example of this. So I'm going to assume today that, well, I'm not going to do that today, but in class we'll give you like a practical experiment. And as the picture suggests, it will involve some sweeties, so maybe even be quite a nice lesson. But today I'm going to assume then that the activity that we'll do in class is done and dusted. But we will perhaps show a bit more evidence of why this is quite useful in class during that activity. Now, if that's the case, I want to do perhaps an explanation of what these binomial hypothesis tests are all about. And I suppose a hypothesis, I mean, it all comes about, as this picture tries to identify, that you've got a problem that you're trying to solve, perhaps, or it might even be best described as belief. So a hypothesis I would describe as a belief that something is true. It's not enough, of course, just to think it's true. You've got to try and prove it's true, and one way of proving it's true is to use a binomial hypothesis test. Now, binomial, you should remember, if you say something is binomial, you're kind of really saying either happens or it doesn't. You should remember doing this. Binomial, you do it an experiment a number of times, that's the n, and the p, it's always the same probability no matter which, how many times you do it. The same probability, constant probability. And at the end of this experiment, I suppose, you have a set number of successes that you've managed to gain from your experiment. And effectively then, having got that number of times, you then work out the probability of getting that number of times. So if I do something 20 times, but only 5 of them turned out to be a success. Now, depending on what I thought the probability of each success was going to be in the first place, will allow me to determine the probability. And you'll notice I have this H0 then, it represents the hypothesis, my belief. And I either end up rejecting it and say, no, actually my idea was wrong. Or I end up saying, you know what, I don't know if I'm right or wrong, but I've certainly not got evidence to say I'm wrong. And that's really all we can do with this. We'll come back to this blue box in a bit. We've got an example under our belt. An opinion poll claims that 40% of the electorate would vote for one of the parties. And I've got 4 party leaders up there from a relatively recent election. A student at a local college suspects that the proportion of young people who would vote for them would be lower. So on that basis, with this student then asked 16 fellow students. Notice there's a set number they ask. This is the n, if you like. And which party they would vote for. Now, I suppose my assumption is always that this belief is right. I assume it's right unless I have other information. So I set my p equal to 0.4. And when they did this test, it wasn't anything like 40% of them. In fact, only 3 of them said they voted for party R. Now, is that good enough evidence to say, you know what, this 40% figure is wrong? Well, let's have a look at the maths. So what will you do here is you end up saying x is binomial, 16, 0.4. And you have to set up what are called hypotheses. They are labelled H0. And you say, well, my belief is that p equals 0.4. But obviously this student believes something else is true. So we have what's called an alternative hypothesis. This, by the way, is called a null hypothesis. But my alternate hypothesis is that b is lower than 0.4. Because that's what the girl, I think it was a girl, she asks, yes. So it asked me to test this at the 10% significance level. That matters as well. And it said 3 of them chose them. So I'm just going to clarify what I mean by p, where p is the proportion voting for party R. There, for R, that will do. So look, I always like to see this as a straight line. And I look at my straight line and I say, well, there could have been absolutely no one who said I vote for this party. And there could have been up to 16 people who said I want to vote for this party. I want to work out what I expected based on my probability. And if you do the expectation, which we label mu, equals the number of people times by the probability, 16 times by 0.4, you get a figure which is 6.4. I would have expected for 6.4 to have said, I vote for party R. Now obviously you couldn't get 6.4 because it would have to be 6 or 7 or 5 or whatever, but that's the, on average, what you'd expect to get. And of course she got 3. Now here's the trick. We always find what's called the tail, with the probability there. And you'll notice it goes from 0 to 3. I go in the direction of the null hypothesis, and it says less than, so I've gone less than 3. And for that reason, I always find the probability of x is less than or equal to 3. Now I do this on my calculator. You should remember how to do this, but I'll talk you through it. It's menu 7, and then we want to press down, so that we don't want binomial PD, we want binomial CD. So press menu 7, then down, then 1. And you always pick variable, which is number 2. And then I can type my details in. My x value was 3. My n value, my number, was 16. And my p was 0.4. So I haven't typed all that in. I get my probability, and it's 0.0651. Now, look, this is a probability. This is the p that I'm referring to here. If p, the probability, is less than the significance level, it says, reject H0. Now, I think it was 10% they wanted me to test. It was 10%. So this, I can write since 0.0651 is less than 10%, we have now got enough information to reject the initial belief, reject H0. And in fact, what we describe this as sufficient evidence. Now notice it's no more than that. It's sufficient evidence that this girl was right. Now I'll word it properly for you here. Sufficient evidence at the 10% significance level that the reported figure is too high for the young people at the college. Now that's why I've got you to see it written down properly. But that's what you'd have to write in the exam. Let's do another question. In a county up in the northeast, it's called County Durham, 6% of the population are thought to travel by bus, train or tram. A County Durham student thinks this figure is too low. Obviously they think it's higher, perhaps because they were students all the time, and decide to test her hypothesis. She asked 60 students. Okay, so I'm getting to and 10 said they came by bus and test it at the 5% level. Okay, so if I just do this here, I would say x is binomially distributed. She said 60, and how many was it? 6% is what we think travel by bus, train or tram, whatever it was. H0 is that p equals 0.06, but she thinks it's higher, so H1 p is greater than 0.06. And technically you should write where p is, and I'll come back to that perhaps in lesson. Just explain where the p comes from. Now, what did we get? Well, we then, having got this, we could have got anything from 0 up to 60. We do that calculation again. We do mu equals np, which is 60 times by 0.06, which is 3.6. Now, that's how many I expected to get this time. But in actual fact, I got more than 3.6. I think it said we got 10. Yes, 10. It's quite a lot more. Notice you don't test for 10, you test for the tail. And the tail this time is to the right because this points to the right. So I find the probability that x is greater than or equal to 10. Now, you may recall that you can't do this on the buttons on your calculator. More than 10, well, it's greater than or equal to 10. The opposite of that is 9 or less. So I'm going to find this number and do 1 minus it. So let's do that now. So type this in. I'm already on it, so it helps. X is, what did I get? I got 9. I've got to type into my calculator. N was 60. 0.06 is my P. And it comes up, alright, it's quite small. Well, this part is quite big, 9971. So if I do 1 minus that, I get 0.0029. In fact, it's 287. That's a 3. And I probably need that for the extra decimal place. But one way or the other, you'll notice it's very small. And what was the significance level? It's 5%. So this is less than 5%. And because it's less than 5%, I reject. Notice this rule. If it's less than the significance level, reject H0. So I can reject H0. Happy days. And then it's the wordy bit. What does the wordy bit look like? It says, we have got sufficient evidence at the 5% level that the figure is too low, this 0.066% figure. Explain whether you think the student was right to test her hypothesis in this way. Well, possibly not, because she may have just tested students at her college. I think yes, she did. And her students at her college probably aren't representative of the general population. And that's what I've written here. They may not be independent. They're probably not representative. Is probably the best way of describing it. Next question. In order to test a coin for bias, a referee tosses it 20 times. Okay, fair enough. So what are we talking here? We're saying x is binomial. He does it 20 times. You expect to get 0.5. Notice, you always say the one for H0, that you can say P equals. I would say P equals 0.5. He is just testing, it seems, for bias. So he doesn't know which way to go. Doesn't know if it's more or less. So we have to say it's not equal to 0.5. This is an example of what we call a two-tailed test. Up to now, we've only ever seen one-tailed test. This is a two-tailed test. I'll carry this on the next slide. So on a two-tailed test, obviously, there's I'm doing it 20 times, so I could get 0, I could get up to 20. Mu equals MP. Won't surprise you to learn it's 20 times by 0.5. You'd expect to get 10 heads or 10 tails. What are we looking for? We actually got 14 heads. So probably I do need on this example to very clearly say, very clearly say what the P is. P equals the probability, let's say, of getting heads. Because definitely it's not obvious this time whether it's heads or tails. Now, I think it said we got 14 heads. We did. We got 14 heads. Is that sufficient evidence to say the coin's dodgy? Well, first of all, we need a significance level. It said that it's 10% significance level. And by the way, I could have done tails instead, but I've chosen to go heads. That's why I've written 14. Now, you will recall as well, this was two tail. I wrote it's not equal to 0.5. I don't know if it was going to be too small or too big. So here's the thing. What you're going to have to do is 14. We'll still calculate this probability. So the probability that x is greater than or equal to 14, that's what I'm going to find. Because it's always go away. If it's a two-tail, always go away from the mean. So there's my mean in the middle. So I'm going away from it towards the tail. And when you do this, obviously this is 1 minus the probability, same as just now, less than or equal to 13. So let's type this into my calculator. N was 20. Oh, I have to put in x first, although I got 14. N was 20 and 0.5 for the P. And this has given me, was that for 13? I'm just going to go back and check. X was 13, I nearly got it wrong. So x is 13, N is 20.5. And I've this time got 1 take away 0.9423. And I think it's 0.0577. This is, in fact, it's greater than 5%. Now, why am I checking against 5%? Just be aware of this. It does say 10%, but notice this is two tails. So on this two-tailed test, I write 10% significance level. But what that means is 5% at each end. Because I didn't know which end to check at. It didn't say whether it was going to be more than 10 or less than 10. I have to check both ends. And for this reason, it's not 10% I check it against. I check it against half of the amount, 5% each end. And for that reason, this is too big. It would have been smaller than 10%, but bigger than 5%. So we write this as do not reject H0. The belief that it's fair coin has to hold, because we have no evidence to suggest it doesn't hold. Let's see the wordy bit then. So P equals a half, P is not equal to a half. I've done it exactly the same way. Do not reject H0. There is insufficient, this is the wordy bit you have to write, insufficient evidence at the 10% significance level, and the coin is biased. Notice I still have 10%, even though I halved it. A question for the lesson. A couple of things we're going to do in lesson now, but after that we'll look at exercise 18b. As you can see, we'll hack through those during class. So best of luck.